Hello everyone and welcome to the Autodesk Robot Structural Analysis tutorial brought to you by the Civil Engineering Essentials channel. I hope you enjoy the video. Right, so in this video we are going to basically talk about the load calculations on those lattice steel structures, and it is going to be a little bit theory heavy because this is very important to understand how those loads are calculated before using those loads in the design of such towers. Because understanding how things are calculated is more important than understanding how to use things. And in this video, my main reference in this video is the ASCE guidelines for electrical transmission line structural loading. Those are guidelines used to calculate the structural loading for those structures based on wind loads, snow loads, and the weights of those power lines. Now, to try to understand basic principles here, I had some drawings prepared for you. So, well, previously in a previous video, I talked about something called the wind span and weight span, as you can see here on the side view, and please refer to that video to understand the differences of those spans. Now, if you have a plan view, usually the power lines could be like this. In that case, the power lines are perfectly parallel and they have the same directions and there is no theta between them. Now, the consequence for this is that the force on the right is going to cancel out the force on the left, meaning that if you sum up forces in X, this force and this force will eliminate each other. And the tension in the cable is usually the same because it is one cable and the tension on the right is going to equal the tension on the left. Now, this is not always the case. Your power lines are not always parallel to each other. Sometimes the power lines are or have a line angle from one side to the other because, your power lines could move in angles. And of course, there is like one case like this or another case like this. And if you have a power line that moves at an angle, then suddenly the summation of forces in X and the summation of forces of Y do not cancel each other out. Here you have zeros everywhere, but here you don't have zeros everywhere. Now, truth to be said, in the ASCE, it assumes such a assumption in the guidelines, and quote unquote, it assumes that the structure is located on the perpendicular bisector of the line angle. So basically, you have half theta on the left and half theta on the right. This is important because the loads on the tower are going to be calculated and comprised from the following loads. The first load that you would think about is, well, the own weight, meaning that a tower has an own weight, and this is something from structures, like the forces on the tower itself are something that any engineer can calculate. You have the own weight of the tower, you have the wind load applied on the tower, and you have all kinds of other loads that a structural engineer can easily calculate and use. So in this video and even in the modeling video, I will be ignoring the wind loads applied on the tower, but I will keep reminding you that I'm ignoring this because I want you to try calculate and apply it on the different elements. What is not being ignored is, well, the loads on the power lines, and this is why we need the ASCE guidelines. Because now you have here wind loads and you have here own weight. So you have the weight of the cable, you have the wind loads from the cable, and you have even cable load imbalances due to the theta here. So let's dissect them one by one. The first one is the wind load. Well, if I have a tower, let me just draw it very quickly here. If I have three towers, for example, so I have tower number 1 here, tower number 2, I'm drawing them as triangles, but you get the idea, and tower number 3 here, there is something called the wind span. Now, the towers basically don't have only one power line, they have multiple power lines, like you have power line like this, a top power line, you might have two power lines like this, which is somewhere here. So for example, you might have 5 or 3 power lines, like those are 2 power lines. And if you have multiple power lines, well, you would think that each power line has its own wind load. And you're right, because each power line is on a different height. And as you know, the wind load is related to the height of the power line. Furthermore, like the power line itself sags, so it has a top maximum height and a minimum height. So how do we usually calculate the wind load for those power lines? Now, you would think that we should take, for example, the centroid of this shape. And you're absolutely right, by the way. If you take the centroid, which is going to be the point where the resultant of the wind is going to act, you can use the height of that centroid to calculate the wind load. But, well, we don't do this because this is too complicated to achieve. So rather than somebody else would say, well, what about calculating the top of the cable here and the top of the cable here, or basically one top of the cable, and assume it to be the ruling height here. And well, each cable has one top, so you can basically calculate the wind load on each cable. Now, this is more of a hassle. It's correct, but what the ASCE code does is it takes the tower. So let me draw a front view of the tower, like you have this tower, okay? And there is like multiple connection points. I'm being very sketchy here. So you have here a connection point and here a connection point, and let's say that you have 5 power lines. You have one power line here, one power line here, and one power line here, 5 power lines, okay? Now, what the ASCE code suggests is it suggests to find the average height of all the power lines, and then basically use this as the height where wind is calculated. That is basically what the ASCE code suggests. And I will abide by this suggestion. I like this suggestion very much. So this is the first question asked and answered. Well, the wind load is being calculated as the average height of the connection of the line at that power tower or tower transmission tower, and this is used to calculate the wind pressure on the power lines. Now, there is more in the SCE code which you can, that's why I suggest you read this, and that's why I might not design the structure today, but next time. I highly recommend you read this because, for example, you would think that those power lines should like gallop, or basically, like, why should the power line not change in height during the wind load? Because when wind blows, well, power lines have the tendency to move somehow right and left. And you are right, and this is a case considered in the code. It's called blowout, wind blowout, and there is a lot of information you can check out there. I kind of like it, so you can test it out if you want. However, in my next video, I will just tell you that those are my calculations and here is my loads. So in the next video, I will just take 5 minutes on applying the loads and then start designing. However, to do that next video, I have to go into like painstaking detail with regard to the loads that I have on my transmission tower. So those wind loads are calculated and they are applied in one direction on the tower. So for example, let's say you calculated some sort of wind loads. And how would you calculate those wind loads? Well, it depends on the code, of course, that you're using, but almost all codes calculate something called the pressure. So let's say that the pressure, for example, this is not only an example, is 1 like kilonewton per meter square. I know this is like a high assumption, or a low assumption depending on your region. I just use this as a little placeholder for now. Of course, I will calculate this in more detail, just assuming a load now. If you have this as your wind pressure, then how would you calculate the wind load on the power line? Well, the power line looks something like this. And of course, the power line has a thickness because it has a diameter, because the diameter of the power line is there. So you would calculate the wind load on the power line, basically the total force on the power line, by multiplying the pressure multiplied by the wind span multiplied by the diameter. This is how you can calculate the resultant force of wind on one power line. Now, of course, this resultant force is basically the force on the entire cable. However, you know that the tower is going to take half of the cable on the right and half the cable on the left. So basically, this equation should be like 2 multiplied by pressure multiplied by wind span over 2, which in the end will be the same equation. So this force is being applied on each and every point where you have a conductor or a cable connected to the tower. So you have those wind loads applied on the tower. Of course, you have also wind loads applied on the tower structure, but this is something I will leave for you. I will leave you to think about this and calculate this yourself. I'm trying to tell you exactly the differences. I'm trying to explain to you the unexpected things in this project. So, well, the first thing is the wind load and using the wingspan, and I think I covered that. You multiply the wingspan by the diameter to find the surface area, and then multiply this by the pressure to find the load on each and every conductor that is going to be connected to the tower. So this is the wind load. Now, this is not enough, because according to the ASCE code, you might need to calculate, depending on your local codes, you might need to calculate like a wind load at 30 degrees angle or something. Of course, in that case, you need to cosine and sine this load to find the load on the tower. That's not everything. So the wind load seems to be okay-ish. There's not much to say here. Now we go to something called the own weight of the cable. Now, to find the own weight of the cable, you need to go to something called the weight span. So if you have a cable and you have its density, and usually it's given as in kilonewtons per meter or anything, if you have the density of the cable, then you would just multiply the density of the cable multiplied by the weight span to find own weight of the conductor and apply it on each and every point. So you have an own weight like this going down, which is going to be the weight of the conductor. The equation to calculate this is going to equal the following. So let me just quickly draw them. The equation to calculate this is actually very straightforward. It is rho, which is going to be the length unit weight, multiplied by half length on each side. So half length by 2 is actually the length. And this is called the weight span. And you calculate this and apply it on the tower. There is something very important to note here, that you should add to this something called the insulator assembly. See, this is why I say I need an extra video just to explain those loads, because those cables are not just connected barely on the tower. No, there is like all kinds of insulator that insulates the cable from the tower, and this insulator assembly has a weight. Now I will show you later some examples for this, but for now I will assume it to be like, I don't know, I'll assume this to be 800 Newton per assembly. But of course, you need to check out your local electrical manufacturer or contractor to understand how much this assembly thing weighs. And I will show an example, by the way, on this. You have found the vertical loads and the horizontal loads from the cables. Well, no, because there is something called the line angle. And now I'm assuming an assumption here. I'm assuming that our tower looks something like this. So this is how the lines are being connected to the tower. The tower basically spreads the lines apart. The tension inside the tower will have an effect on the tower. If the line angle would be 0, then there is no effect of the tension of the cables on the tower. Of course, here this is another idea, an option. For now, I will explain the effect of the line angle on the tower using this drawing. And of course, once this is explained, you can of course use the same engineering sense to calculate any type of cable connection on the tower. And this is, I told you, this is like where the surprise is. Like, there is a lot more detail than you thought. Wait until I reach something called the failure containment load, which is really cool when I reach this. Of course, don't mind the background noise because I'm somehow not at my usual recording place. Now let's take a look on this one. Now this cable is under tension, obviously, and this cable is under tension, and all those cables are under tension, basically. Now this tension here is, well, they should actually eliminate each other, but they don't. What eliminates each other is the cosine component. So tension cosine theta, I will call it right now, or tension cosine theta over 2 will eliminate each other because, well, the tension is equal and the theta is equal. This is not always the case because, for example, in this case, they don't eliminate each other in this case. So you need to be careful when you say they eliminate and when you say they don't eliminate each other. With that being said, well, let's consider the idea we have here. Now, in this case, the t cosine theta over 2 will eliminate each other, so there is no net forces on the tower in the x direction. However, in the y direction, you have net forces because suddenly you have here two forces which are going to be like 2 multiplied by t sine theta over 2 from that side, which is going to be an upward force in this case, but of course in reality it's an inward force and a force going inside of the tower. So I basically use this to denote for the force. This is one force. And you have here an inward going force, which is going to be the same value, t sine theta over 2 multiplied by 2. I think I wrote something wrong here, so let me just fix that. Yeah, okay. So it's basically t sine theta over 2 multiplied by 2 inwards to the tower. So, well, there is a lot more than I thought about the cables, right? That's not all, because you have something called the failure containment load, and you have something called the snow load. Now, for the snow loads, truth to be said, I live in a region where there is no snow load, so I would not be the best to basically talk about snow loads in that regard. However, you can calculate the snow loads and add as a separate case for the loads on the assembly line, on the conductor. However, in my case, I will ignore it because I don't have any snow loads here, and I like to be 100% sure of an information when I give it. So anyway, there is no snow load here, but the last thing is something called the failure containment load. When a cable conductor fails due to any reason, there could happen something called a consecutive collapse. What does this mean? Well, think about it, and there's a very good reason behind something called the failure containment load. Now, let's say we have those towers. I want to draw them a little bit smaller because I want to draw many of them. So I have those towers. Don't mind my accuracy in drawing. And I have this special tower, which I color in red or in some color. I'll continue drawing my other towers. And of course, I have those towers, and those towers are connected with power lines. Now, let's say that a catastrophic event occurred. And for some reason, the power lines here just broke. Like those power lines, for example, those power lines just broke. Now, what happens if those power lines break? Well, let's take a look on the tower here in dark red. Let me just draw it again here for you in dark red and talk about this in detail. So if you have this tower and you have suddenly a catastrophic event on the cables, then you have all the forces from one side and no forces from the other side. You only have a cut cable here, like it's just lying on the ground, right? So you have all kinds of problems here because suddenly, if those cut, you have the tension on the other side. Now, this is a problem because suddenly the tower is under loads that you have not accounted for if you don't know this failure containment load. So in that case, if you don't design the tower for those loads, you will have extra loads that cause bending and cause all kinds of problems that could make this tower fail. Now, if this tower fails, well, then the same thing happens to the other tower because the loads will basically propagate, and then this will fail, which will cause the next tower to fail. And you see a lot of those hurricane aftermath pictures where you see a lot of towers leaning on their side. Now, this is totally normal. You would think, wait, if we know about failure containment, why do we still see consecutive failure in towers? Well, you see, you don't design all your towers to contain the failure. However, you select a few selected towers to be ready for such case of failure. So it's actually more economically feasible to design some towers to be or act as a failure containment tower and leave the rest to not contain the failure. So for example, if something happens catastrophic to this one, then it might be economically cheaper to allow those two things to fail and stop the rest of the network to fail by designing those two towers to act as failure containment towers. Now, if you have failure containment towers, then the load on the tower, especially the tension in the cable, is going to be from one side, and you have to design this tower from one side. Speaking of tension in cable, I haven't said so far what the tension inside the cable is. Now, this should be given in the data of your conductor, and truth to be said, this is really technical now, and you need to consult the manufacturers here. The tension inside the cable depends not only on the sag and the length of the cable, but it also depends on the temperature under which you are designing your structure, the working temperature. So there is a lot more from where that came from, and you should check out this guideline. However, let me just show you how I would design, how I would calculate this. So if I have the tension inside the cable given, then everything seems to be fine and I can use it directly. In this document, for example, what is given to me is, well, I'm given the ultimate tensile strength, which is in kilonewtons. So I'm not really given the working stress or working force. I'm giving the ultimate force. Well, it doesn't matter. If I'm given the ultimate force, well, I will just use it to assume this to be my T in the tension. Some other design sheets might give you something called the F ultimate, the ultimate stress inside the cable. Well, if you're given the ultimate stress, you just multiply the ultimate stress by the area of the cable. So, I mean, you can use this to calculate the loads inside the cable. Now, I don't want just to quickly sign off like this because you're not used to this. Like, I should show you some more interesting stuff. So in the reference I have given you, there is something called an example. And this is gold because now you can see everything. Like you can see something called reliability factor, ruling span, wind span, weight span, line angle. This is the angle between the lines, by the way. The insulator assembly, the weight of the insulator assembly, 200 pounds. the weight, lots of stuff that you can. Of course, here we have another tower, but I'm not going to model this. I modeled a different one. But here is where the gold is. Now I'm gonna very quickly walk through this. I'm not gonna take too much time here. But now, first of all, it calculates the wind on the wires. Now you see here he has 5 wires being applied on the tower. So he is calculating, first of all, the average wire height, which is 3 multiplied by the level 74 plus 2 multiplied by the level 89 divided by 5. He gets here the 80 feet. Of course, he references also the equations and chapters used in this guideline. This is gold because now you have not only an example in video form, which we were going to do on robot, you also have the design material that you can use for your career. And I think, I don't want to brag, but I think this is what like makes this channel stand out. Because look, I'm not really here telling you only how to do this, like you do this by doing this. No, I actually like try to go to the base of the things so that you can have a nice little library for the future. Anyway, the 80 feet here is the height of the cable. Of course, this is in US customer units, but you can easily switch it to SI units. Then he enters something called the calculations for wind pressure, and this is where your code will change. It depends if you're using the British code, the Euro code, or the ACI or ASCE or whatever code. So here he's calculating the wind pressure, which is going to be 16.3 pounds per square foot. This is the pressure on the cable. Now he wants to calculate the wind load on the cable, but before that he shows you the wire data. The wire data is, well, the data that he got from all kinds of manufacturers. You can see that he has some cases, and notice that he's assuming temperatures, because temperatures will change with other things, among other things, will change the tension of the cable. Of course, for example, here in ice, you will have less temperature. And of course, what is this? You can see that those are the requirements here. The NESC is the National Electrical Safety Code. This is a local requirement in America, which might not be applicable for you. CNM is construction and maintenance. And finally, FC, which is the failure containment load. Like if a catastrophe happens, how will you contain that failure? Now, strangely, he doesn't assume a wind load, but still, okay, fine. This is what the code does. Now, notice the information of the ACSR rail conductor. You have a diameter for that conductor, and you have a unit weight for that conductor, as well as the tension. This is what you need for the conductor. You need this, the diameter, because you want to calculate the wind loads. You need the weight of the conductor, because you want to use it for the weight span. And you need the tension of the conductor, because you might calculate a resultant force if the cable has an angle. In this case, it has, because it has a 5 degrees angle. So far, so good. With that being said, let's continue now. You can see here that he starts calculating his stuff. I'm interested in the conductor load. You have something called the vertical load. The vertical load here is the unit weight of the conductor multiplied by the weight span plus 200. The 200 here is the insulator assembly, and you have the transversal load, which is 16.3. This is your wind pressure multiplied by the diameter multiplied by the length, because he wants to calculate the projected area to the wind. And suddenly you see this. Now this is the load due to the cable not being parallel. So he has this, and even I think that he has, as I see from the ASC code, I think that his case is a little bit different. I think that his case is this. I see him only adding. So I think his case looks like this: 1, 2, 1, 2, something like this. Because he is adding the tension to the wind load, because the wind load goes in that direction. And he is adding the tension in both sides. He's adding the tension load to the wind load. So I think that this is the cable assembly he has. Because in my case here, I would on one side add to the wind load, and on the other side I would subtract from the wind load. He doesn't do that, so I think that this is the case he has. And that's what I mean by look at your case before you leap. So you have to look at your case and then decide how you would calculate your tension forces, how would calculate the forces on the tower due to the tension in the cable if they are not parallel. Anyway, continuing here, you can see that he calculates the conductor loads, and finally he calculates the window structure. This is what I will leave for you. And there is also the failure containment load. Let me just quickly check that, because he calculates all kinds of cases. So I'm trying to find the failure containment load here. Yeah, there we go. This is the failure containment load. He starts with this, and he says, well, we have a broken conductor, and a broken conductor means there is nothing with regard to wind and radial ice. So he starts by this. You have a broken conductor on one side, so you have a vertical load only from one half because only one conductor, because you have breaking on one side, you have only the other side which works for you. So you have only half of the uh, conductor applying a load on the side. Also, you have transversal loads due to tension, and notice that he is multiplying this by 1 because you have only one cable. You also have the lateral forces. So let me explain to you what those are, those three letters. The first one is V. V is the vertical load. It's the weight of the conductor, the weight of the cable. You can see that he multiplies 1,800 over 2 because one conductor has broken. So you can see half of the conductor vertical load because one of them has broken. You can see the transversal load, and suddenly you see another load which has the cosine here. Because if one of the conductors break, then you don't have a balanced load in the x-axis, and suddenly the cosine of the load will act, and it will be a large load. And this is the load that the failure containment structure has to resist, because when you on all 5 break, then you suddenly have the tension on one side and no tension on the other side. This is where the danger is. Anyway, I think that this summarizes everything with regard to loads. I know I was thinking I'm gonna start modeling today and finish everything, but it turns out there is so much more details about loads. So I thought, no, I don't want to wing it. I want to keep the quality as high as possible. So I think I'll just upload this video, which might be, I don't know, 25 minutes long. This is a full theory video, so pardon that. However, I hope that you have still enjoyed this video, and next time I will not be wasting time in explaining the loads. I will just implement the loads immediately. I will have them pre-calculated for you, or maybe I will calculate them very quickly for you. So I hope that you enjoyed the video, and this basically is the most important video amongst all because, well, if you know how the loads are, then the rest is just engineering sense because you know how to design steel structures. With that being said, thank you very much for listening, and I hope that you enjoyed the video. Of course, if you have enjoyed the video, please consider liking, sharing, subscribing, and commenting, especially subscribing because it helps increase the reach of the channel. As per usual, this is the Civil Engineering Essentials channel, and we'll catch you in the next video.